Hello, it's 6 o'clock. We'll wait for 5 more minutes, then we'll start today's class. So since two people are there, it's already 6:05. Let's start to discuss. I'll share my screen. Just a second. Can anybody respond if you are able to see my screen, lecture 11, and hear me properly? Are you able to see the screen? Can anybody please reply if you are able to see my screen and hear me properly? Selva, are you able to hear me and see the screen? There is no reply. I hope I am clear to you guys. So I'll start today's class. So this is lecture 11 for this course of material characterization provided by Dr. S. Sankaran from IIT Madras. And this is me, Dorothy Susdeva, the TA of this course. And I'm pursuing my PhD from MRC department and at Indian Institute of Science currently. So in the last classes, we were discussing about the audio is not clear. Just a second. Are you able to hear me now properly? Please reply so that we can start. Are you able to hear my voice clearly now? Is it fine now? Is it fine now, Silva? There is some echo, I guess. But now I have shifted my screen to some other place. And now it is fine. Let me change my place again. Yeah, now it's fine. Please reply if it is fine now. Is it fine now, anyone? Nitin or Seva or anyone, please reply. I hope it's fine now. I'll start then today's class. If there is still any chance, please let me know. I hope you are able to see my screen and I am visible, audible to you. If there is still any problem, do let me know in the comment section. Otherwise, I'll start today's class. According to me, I've changed my place and now the network should be fine over here, I guess. So, from the past few classes, we have been discussing about the diffraction and how this diffraction is happening in the TEM and how TM helps to analyze your samples and different techniques and different ways in which you can have your diffraction pattern in TM, your EBSD patterns, your phase contrast, dark field, bright field images, and all. Is it fine now? Also, there are these when your electron beam falls on the screen, then you have to deal with your astigmatism and stagnation. So, this astigmatism, when your beam is completely circular, like in the case 1, that is the perfect beam. But if you have the under focus or over focus, that means bright and dark fringes. Suppose this is your beam or this is your sample, and if you have a little brighter region, then these are known as Fresnel fringes. Yes, Selva. Selva, you have raised your hand. Do you have any doubt? Selva Murugan. Selva Murugan, do you have any doubt? Then you can ask. Otherwise, please lower your hand. My voice is not audible. Is it for all or only for him? Okay. Am I audible now? Okay, then. I'll start then again. Now my screen is also visible and I'm audible to you guys, right? Just give a thumbs up, anyone? Not clear. Let me try to reconnect then. Yeah, I have rejoined the class. So I hope I am audible to you guys now and the screen is visible. If yes, then please do reply. Am I audible? Why this is issue is happening in this class? The rest all classes went very fine. Can you please reply if I am audible now? I have lowered the fan volume for the interruption. Please tell me now. I hope it's clearer now. Is that sound interruption sound is went or it's still there? Are you able to hear me? Please reply. I don't know what's the problem today. Let me sit in some other area only. Yeah, now I have changed my room itself. No, it's fine. Now it's fine. Guys, please tell it's fine now. Are the same issues there? There were a lot of things to be done today. Please reply so that we can start today's class. Is it fine now? Okay, thank you. Sorry, everyone. There was some technical issue, I guess. I was doing similar kind of meeting only as I did in the previous classes. I don't know why today's class this all thing happened. So if everything is fine and my screen is visible to you guys, let me start today's class once again. So in the last classes, we were discussing about the TEM and how the diffraction pattern takes place. And also we discussed about the bright field and dark field imaging in this. Also, I wanted to tell you about these Fresnel fringes. Like if you have a sample like this, the bulkier one, and then you can have the light and dark fringes just outside your specimen image. So these fringes are known as Fresnel fringes, and these, when under focus, these fringes occur only when your specimen is not focused. So if it is under focus, then you will have bright fringes, and if it is over focused, then you will have dark fringes. And astigmatism, objective lens astigmatism occur if the objective aperture is misaligned. So you must carefully center the aperture on the optic axis symmetrically around the electron beam to form the bright field or dark field image. Your astigmatism of objective lens, if it is completely correct, then you will have this circular beam on your fluorescent screen, and if you converge and diverge it, and if that means increase or decrease the intensity, then it will uniformly go in all direction. But if it is astigmatic, then it will go like this. So that means it is and other way it will go like this, once here and once here. So but it should go uniformly in all the three directions. So if it is going uniformly, then we can say that astigmatism is being corrected. Also, we have discussed about this camera length in the previous classes. I wanted to discuss that how this camera length RD is equal to lambda L being derived. So this camera length is basically in the diffraction pattern when you have your incident beam is, sorry, when you have your incident beam following on your specimen and it is getting transmitted and the other beam is getting diffracted, then your you will have the diffracted spot as well as the direct spot. So the distance between the diffract spot and the diffracted spot is given by capital R, and the angle between the diffracted spot and the direct spot will be 2 theta. And as we and camera length is basically what, the distance of this uh, direct spot to the specimen. So this L1 is your camera length. So the angle between the direct beam and the incident beam is 2 theta. We already know this one. And from the Bragg's law, we say that sine theta is equal to lambda by 2d. And since theta is very small, we can say sine theta is approximately equal to theta itself. Also, we can say using this by considering this triangle which I am marking right now. Yeah. So using this complete triangle and taking this as the angle 2 theta, the tan 2 theta value will be this perpendicular r divided by base L. So r divided by L will be equal to tan 2 theta. And since this is small, so we can write tan 2 theta as 2 theta. And when we compare these two equations, that theta is equal to lambda by 2d and 2 theta is equal to r by L. On comparing these two equations, we will get 2 theta is equal to r by L, and from this we can write 2 theta is equal to lambda by d. So comparing these two, we will get r by L, sorry. We will get R by L is equal to lambda by D, or we can directly write RD is equal to lambda L. So this is basically your formula for. So if you have your uh, wavelength, you already know, d spacing of your material, you know, you can calculate the r distance from your diffraction pattern, then you can find out the camera length. So if we increase the magnification of lenses between the specimen and the viewing screen, we increase the effective distance L between the specimen and the screen. So when you are in the diffraction mode and then you are increasing the magnification of the lens, then you are just increasing this L distance between the specimen and the screen. So basically, when you are in diffraction mode, magnification means increasing camera length L. Okay. Then we have these elastic and inelastic scatterings present in this TEM. So elastic scattering is basically what? When you have your nucleus present at the center of your atom and your electron beam, electron clouds is present all over around it, the nucleus, and your electron beam is coming and it is being diffracted by the nucleus with the interaction with the nucleus and go as it is. And if it is very far away from the nucleus, then it won't have any much contribution from the nucleus and it will go like this. And if it is going in between, then it will be slightly shifted with the angle, certain angle from the incident beam direction. So scattering is basically what? It changes the direction but not the energy. So basically elastic electrons electron interaction usually result in a relatively low scattering angle, while electron-nuclear interaction causes high angle scattering. So when the electron and nucleus are interacting, it is having a high angle scattering, and when the electron cloud is interacting with the incoming electron radiation, then thus you have the low scattering angle. Also, this is just a small demo for the Fourier transformation. Like basically you do Fourier transformation of your image to see if you have properly aligned or not. So what is Fourier transformation? Fourier transformation is basically any function which can be written as the sum of periodic function. Like in this case, the time domain can be represented in terms of frequency domain. So in this case, we have the real space can be represented in terms of the reciprocal space and so on. So if this is your main function, so this is this red one, so it is just a combination of this cos nx plus b sin x. So these all blue ones which are shown here are all summing up to get this red wavelength. Fourier transformation is just a mathematical form to represent some time domain into some frequency domain. Like you have your frequency with in real space like this with up and down. Then when you do the Fourier transformation of the same, you will get the frequency space. Like we said here, the time domain will convert into this frequency domain. For example, if you have your fringes corresponding to this one, then your Fourier transformation will be corresponding to the d-spacing of this, and since this is all similar, it will just be some two spots. And you all know this, if this is the real space and this is your reciprocal space, then here you see this d and this d. D is large, so in reciprocal spacing distance will be small, and here d is small. In reciprocal space distance will be large. Similar in this case, here the d spacing have been increased to very high. So in reciprocal space, the spots are quite closer to each other. And in the last case, you are having multiple fringes. So each fringe will correspond to different, like this one will correspond to this small one. Okay. And these small fringes will correspond to this. These will be in the similar direction to the your fringes in the real space. So basically, this also be discussed in your XRD, that you have your crystal, and basically in diffraction pattern, what you are doing, you are just projecting your three-dimensional object in a two-dimensional object. Suppose in your atlas also, your earth is completely, your globe is spherical, and in atlas it has been given in two dimension. So that means that the suppose if this is, here somewhere is India and here somewhere is USA. So if you want to go directly from India to USA, you can follow this straight path. Everyone will think that this is the shortest distance between India and USA, but this is not the case, because we are thinking this in two dimension only. We are not considering the third dimension. Since the globe is very circular, the shortest distance will be one which will be traveled in this circular path. So this one will be the shorter distance. This a person can understand only when he or she understands how the three-dimensional object is being represented in the two-dimensional object using this stereographic projection. And we use this wolf net to tell which this is very useful in your diffraction pattern analysis and everything. Suppose this crystal, the center crystal, is your basic crystal, and it have different kind of planes, and suppose these planes, so firstly from each plane a perpendicular line is drawn, like suppose from this a perpendicular line is drawn, and that line is being projected onto this plane of projection. So this is one plane of projection, this is 2D, but this crystal itself, it is 3D. So we are just representing this crystal from three-dimensional to two-dimensional to better understand and to see, draw it in the paper and see how we can imagine it. So basically, each and every plane have a projection on this outer plane, and then it will, suppose you are having this plane, the normal, suppose you are having this plane, the normal to this plane will be somewhere here, and then you will join this point to the lower point, this line. So the intersection of this line with this plane of projection, this point will tell you about the plane or the direction of this plane. So this is little bit tricky. I hope you all have read this in your XRD classes and how we can use this stereographic projection. So this is basically a standard projection where you can see that if your atom is along 0, 0, 1 zone axis is represented by direction and direction is given by this square brackets. So the central spot will be your 0, 0, 1 and the spots 1, 0, 0 and 0, 1, 0 will be 90 degree to this plane and 90 degree to each other. So these in this zone axis 1, 0, 0 and 0, 1, 0 planes will be present. So here are those two planes and these two are 90 degree. This is and also you will have the inverse of this bar 1, 0, 0 and 0 bar 1, 0 also present, and in between these two 1, 0, 0 and 1, 1, 0 you will have 1, 1, 0. So similarly you can have all the family of planes which will be present in this 0, 0, 1 zone axis. So 0, 0, 1 zone axis means all the planes which are perpendicular to this zone axis will be present in this diffraction pattern. Fine. These are some standard cubic stereographic projections. The pole in the center defines each projection. So these are, so the first one is 0, 0, 1, which we already discussed, and the next one is 0, 1, 1, and the next third one is 1, 1, 1. So these are some of the standard stereographic projections which you can see to understand and do the indexing of your diffraction patterns. So if you have for the indexing of your diffraction pattern, let me zoom one of the diffraction patterns. Suppose this is red one is your central spot, then you have to determine at least three. If you have determined two direction non-linear, then you can tell all the other points or all the other spots in your diffraction pattern. Okay, suppose this is your M and this is your L. So you have calculated this distance M and this distance L. So the ratio of these two distance is 1.414. Then and for the cubic system, this zone axis will definitely be 0, 0, 1. As you can see that your M is having bar 1, 1, 0 plane, and so the distance will be under root of 1 square bar 1 square plus 1 square plus 0 square, that will be under root 2, and for L your distance will be bar 2 square plus 0 square plus 0 square, that will be under root 4. So the ratio of L is to M will be under root 2, so that if you just find out the ratio between the non-linear planes in your diffraction pattern, then also you can find out the zone axis. So similarly in the next case you have your M is represented by bar 2, 0, 0 and L is represented by bar 2, 1, bar 1, this one. So now the ratio of L is to, in this they have calculated the ratio of L is to N. N is 0 bar 1, 1. So the ratio of L is to N is 0.732, that is root 3, and ratio of M is to N will be root 2. So in that case you will have this 0, 1, 1 zone axis. Also you need to see the angles as well as the distance. So firstly, you have this diffraction pattern. You will calculate the distance of these two non-linear vectors, either nm or ml or nl. You can find out nl, ml, nm, because all three have these different angles and all are non-linear. So you need to calculate the distance and the angle between these two, distance and angle. So if all these satisfy, you can just practice the for the standard samples. Like in the third one is bar 110. So in this case, you will have your, also you should remember that in your about the reflection, forbidden and allowed reflection, forbidden and allowed reflection, just as we discussed in the XRD. For the FCC, your HKL conditions, and for BCC, your HKL conditions are different for allowed and forbidden. So in this case, 100 is not allowed. So this spot won't be present. So if you are seeing this 200 spot, then there should not be any spot halfway between the direct spot and 200, because in this case 100 doesn't exist. So you should remember these rules, and you can have the standard look at the standard diffraction patterns in these cases. These are some more standard diffraction patterns for the crystal, which you can have a look and just try to index them using the distance ratio and seeing just the angles. This we have discussed in the previous classes about the Kikuchi lines. That Kikuchi lines are formed by the inelastic scattering of electrons, which then subsequently be elastically scattered. Elastically scattered means what? Back diffracted by these lattice planes. So for these, to observe the Kikuchi lines in your on your screen, the specimen should be thicker with less defects. If the specimen is very thin, then you won't be able to see the Kikuchi lines. You will only be able to directly see your diffracted spot. For thin specimen, you can directly see diffracted spot. But for the tilting and everything, because these Kikuchi's lines are what? These are the road maps which we discussed. This will tell you in which direction to move to get in the exact zone condition. So if you are in the exact zone condition, only then you will see these perfect, beautiful diffraction patterns. If you are slightly away from the from the zone axis, then you will see some distortions in your diffraction pattern, and that could be misunderstood. So you always need to go to the exact zone condition and then determine the diffraction pattern, and that will be done using this Kikuchi lines. So Kikuchi lines, we know, are these two lines. One is this excess line and one is this deficient line. One will be, and in the diffraction pattern, we have the excess line is, suppose this is your direct beam and you have your Kikuchi lines like this. One is your excess line and one is your deficient line. So please remember that in your diffraction pattern, the excess line is very away from the direct beam as compared to the deficient line. So this deficient line is closer to your direct spot as compared to the excess line. So in this diagram, you can clearly see that you are able to see these diffracted spots along with this central spot, and also you are able to see these Kikuchi bands as well, right? So all these bands are visible. So one line will correspond to theta b and the other line will correspond to minus theta b. So one is the G Kikuchi line and other is will be the bar G Kikuchi line. Neither of them will be the zero Kikuchi line. Okay. So tilting and Kikuchi lines. So if we tilt that, this I have already told you that if we tilt the crystal through a very small angle, the Kikuchi lines will move, but the intensities of the diffraction spot will hardly change. And the positions of the spot will not change. So Kikuchi lines are much more sensitive to beam specimen tilts than spots in the diffraction pattern. So for the movement or for the tilting of your specimen, you always require your Kikuchi lines because these are very sensitive. So these are basically just the road maps. So if you want to go from 101 zone axis to 001 zone axis, then you can see that you will have the uh, three lines which are interacting. Suppose these are the three lines. So the line, sorry, there are four, no, this one, this one, this one, and this one. So the line which is corresponding to 0 to 0 plane, you need to follow that line. Only that line will take you to the next zone axis, which is 001. So how will you know that you are following the 0 to 0 line? So that you will know by experience because the thickness of the all the lines you can say that the family of planes are different or not. And similarly, if you want to go from 001 pole zone axis to 011 zone axis, then you need to follow again 200 because this 200 plane is common in this 001 zone axis as well as in 011 zone axis. This is the common plane. So you need to follow this plane because this plane will exist in this zone axis as well as in this zone axis. Suppose this is your central spot and this is your HKL. Then the further spot, the next spot will be 2H2K2L because half, if it is half, then only half of the plane it will be present in between the diffraction spot. But HKL cannot be half further, so there will be no spot between the direct beam and the HKL. So only if it is 2H2K2L, then there might be spot in between which can be HKL. So this is again the Kikuchi line map for your FCC crystals. So for your FCC crystals also you will be having 001 zone axis and you can follow any of the road to go to some other zone axis. But remember that there is certain limitation in your instrument. So if your pole pieces are very close, you have to put your specimen inside the instrument like this, and if your distance between the pole pieces is very small, then there is some restriction on tilting of your specimen. So you need to keep this in mind. So there is one alpha tilt and there is one beta tilt. So alpha tilt is what? Suppose this is your specimen, your alpha tilt will be in this direction only. This will move, this one. So this is your alpha tilt, and your beta tilt will be one where your specimen will be moving in this direction. This is your beta tilt. So generally it's seen that when you are doing this alpha tilt, then you are not you are just rotating the goniometer itself from going like this, and in beta you are completely, this is, suppose this is your specimen holder, you are completely tilting it in this direction. So then you are changing the Z also. Just the Z value is also changed. So when you are doing this beta tilt, then you always need to correct your Z value in order to get a good quality image, or in order to understand whether you are going in the right direction or not. Then we'll discuss about this factor S. So basically, you have your deviation parameter S. You already know, we discussed that in when your specimen mm, is in nanometer regime, you have railroads in the reciprocal space. So basically, the spots which you are seeing is in the diffraction pattern is not one single spot, rather it is the elongated rod in the perpendicular direction in which it is in nanometer range. Okay, so these are the railroads, and we told that the Bragg condition will be followed only when your evolved sphere will pass through this diffracted pattern, diffracted spot. So if your evolved sphere is like this, then your diffraction spot is now passing through this evolved sphere. That means it is following Bragg's condition. That means it will be diffracted. But if your evolved sphere is like this dotted one, then you can see that your diffracted single spot is not touching, but the railroad is touching. So in real reality, these are not one single roads, rather they are these railroads. So even if the evolved sphere is not completely touching the center of this direct spot, that will give you the diffraction, because this is not one single spot, rather it is railroad, and you will have your, and there will be much more region in which the evolved sphere can touch this railroad to get the diffraction beam. So suppose by looking at this diagram, when you have your specimen like this and your incident beam falls, and this is your incident beam, and as we know, this is your evolved sphere, the radius will be given by 1 by lambda and all. Suppose this is your, this is your diffracted spot, and your evolved sphere, this one is touching this, and then suppose your evolved sphere is touching this, that means it will be getting diffracted. And suppose the evolved sphere is this one in this case, then there are two conditions. So this deviation from the exact Bragg condition is given by this deviation parameter S, which is either positive or negative. If it is zero, that means it is following exact here, but if it is outside of the evolved sphere, then S is greater than zero. But if it is inside the evolved sphere, then inside the evolved sphere, then your S is negative. And if it is outside, then your S is positive. So they see this planar view of this diffraction pattern, this one. Suppose this is your direct beam and this is your S is equal to 0 line. Then you will have the deficient and the excess line. So deficient line is much closer to this S is equal to 0 as compared to the excess line. And deficient line means S is greater than 0. And the excess line means, sorry, these are just the deficient and excess line at S greater than 0. That means outside the evolved sphere only, because this will give the two Kikuchi lines. One will be deficient and one will be the excess. One deficient will be closer to S is equal to 0 and the excess will be further away as compared to the deficient line. So similarly, we have shown in this case, suppose the wedge-shaped specimen is there, this one in figure A, where your beam is following in this direction, and then you have your S is equal to 0 like this, and then in the inwards your S is negative, and outside the evolved sphere your S is positive. So then your specimen is giving, after this direct spot, it is giving excess and deficient lines at both S is negative and when S is positive. So these will tell you about the Kikuchi lines from the S greater than 0 as well as from the S less than 0. And this I have already told you that the railroads are basically always normal to the surface. Suppose this is your sheet, then your railroads will be in this direction. I guess I need to speed it up because we need to do questions also today. A lot of time got wasted. So I'll discuss faster, then we'll go to the assignments for this week. So this is the exact Bragg condition where this is your direct spot at O and this is your diffracted spot. And in this case, you won't see any diffraction pattern on your screen. But if you are having your S is positive, that means it is inside the evolved sphere, and S negative means it is outside the evolved sphere. Then it will be shifted from the direct beam. Also, you can have this when your S is negative, then you can have this symmetry condition. Then you can have your positive G as well as the negative G. So this will give you the Kikuchi lines and then you can find the diffraction pattern in this case. Then we'll discuss some, we have already discussed about the convergent beam electron diffraction in the previous classes. So here basically TM works in the parallel beam mode. TM works in parallel beam mode. Remember, if this is your specimen, then your incident beam should be almost parallel. But CBED is convergent beam electron diffraction. So there you need to converge your beam and then it should fall on the specimen, and then each diffraction spot will consist of the Kikuchi lines, and that will tell you about a lot more information about the specimen orientation and all. So here the convergence angle will be this one. So to form a CBD pattern, you have to create a small beam with a convergence angle, semi-angle alpha greater than 10 milliradians. There are at least 5 microscope variables you need to control to form the CBD pattern. First, the beam convergence angle, this angle alpha, the camera length L. In diffraction, we can change it using the magnification, or also the size of the beam, the probe diameter should be small. The thickness of the specimen should be higher. The focus of the pattern, whether it is under focus or over focus. So these are also known as this causal molestant K, or basically your KM patterns. So this basically is shown that how on changing the C2 aperture size, your CBD pattern, seabed patterns will change from one discs, individual disc, to completely with the overlapping of all the discs, like in this F diagram. So when you are having the smaller aperture size, then you are having the individual spots separated. But as you are increasing the C2 aperture size, your diffracted spots are getting converged and you are getting this CBD pattern, and at last you will get this CBD pattern on the TM screen with this high C2 aperture size. So this is just the same thing. This we already discussed, that with the S is equal to 0, will be the line of exact break and reflection, and you will have your positive and negative values of S, where your diffraction would be visible, diffraction spot, because this is your railroad, and even if your revolved sphere is passing through this direction instead of this exact point 2, then also you will see this diffracted spot. Also, we'll discuss little bit about this thickness fringes. So basically, the sample can have thickness or bent contours. So if your sample is bent uniformly, bent in certain direction, or it is having thickness difference, like in this wedge, if you are having this sample, wedge sample, wedge like sample, then there is this thickness difference. This is thicker and here the specimen is very thin. So then you will have this bright and dark fringes. In the bright field, you will have this bright fringes appear due to this thickness variation in your specimen. So this is basically given by this characteristic length, or we can say this extinction distance we discussed. So this characteristic length for a diffraction vector We can call it basically the extinction distance because for the property we'll discover it later. Note that this is your characteristic length is basically a scalar quantity and it depends upon the lattice parameters Bc and the atomic number and the energy by which you are exciting your electrons. So this is basically the formula which is used to represent the characteristic length for the given system. This professor have already discussed. So this will result in this. Also, we'll discuss about this Howe-Venn equation. So this is basically the mathematical formalization for calculating the intensity. So you are having the kinematic diffraction as well as the dynamical diffraction. So there are multiple diffractions which are present in the system. There will be only one direct beam, but there will be multiple diffracted beams. As we discussed in the dark field, that we can have multiple dark field images, but bright field image will be single only because you are having the multiple diffracted beams. So in that case, you can select, suppose this is your direct spot and these are your diffracted spot. So you can select any of the diffracted spot to have your dark field images, either one or two or three, but your direct spot will be this one only and this one will give you your bright field image. So two beam conditions, is it possible to calculate? So there is one two beam condition where you can do the imaging of your defects majorly, because two beam condition, suppose this is your direct spot and this is your diffracted spot, then you will move your sample in such a way that your diffracted spot comes in the center, and now your Kikuchi lines, earlier your Kikuchi lines were like this and your aim was to align or tilt the specimen such a way that you are in the exact zone axis condition. That means at the exact center of these Kikuchi lines. But in the two beam condition, you should be at a certain distance in which direction you want to take. Suppose in this direction you want to take, then your center of the beam will be present in this direction for this two beam condition. So now the defects which present in this family of plane which will be, so after doing this as the center and then doing the imaging, then the defects or anything which are present in this plane will be visible. So if the defects are present in this plane, then you can clearly see them in the image. And if your defect is present in some other plane, then you can go to that beam. So this will be basically your two beam condition, and it is given by the this Howe-Bellman equation, where you have these two equations. This sir has discussed already in the class. I won't discuss it much further. Also, you have this thickness and bending effects also present in your system, which is given by this Ig and S effective. So varying the T while keeping the S constant, giving the thickness fringes, and varying the, so this is just a combination. So varying the S while keeping T constant will give you the bend contours. So this is, This sir has, I guess, already discussed in the class. We'll focus more on the questions part in today's class. So these are all the bent contours. So if your specimen is bent in this direction and this is your diffracted beam, then you will get the positive as well as the negative G values. So like this you can have. If there is any doubt, please let me know because I guess we have wasted a little bit in time in the starting due to that some network interruption. I wanted to discuss the question parts because the lecture have been already discussed by professor very clearly in the class. If you have any doubt, please let me know. Otherwise, we'll start the assignment of this week first. So question, if there is no doubt, if there is any doubt in between, you can raise your hand and let me know. If there is no doubt, then I'll start the practice assignment of this week 11, which says the fringe contrast depends on the sample thickness. Is this statement true or false? If you have studied the professor's lectures and have listened to me, you must answer this question. This is very simple question. So for the fringes contrast, it will depend upon the sample thickness. Just now we discussed in the last slide only. Yes, it will depend upon the sample thickness because you have your thickness fringes are present in the specimen, just as we saw in this case, this one. Okay, so this statement is true. The next statement says, question number two says, if the specimen thickness is dash, only spots will be seen in the diffraction pattern. If it is very dash, only Kikuchi lines will be seen. So we already discussed for the Kikuchi lines, your sample should be thick enough and your diffraction spots will be seen in your thin specimen on itself. So if specimen is thickness is thin, only spots will be seen in the diffraction pattern. If it is very thick, only Kikuchi lines will be seen. So there should be some optimum thickness of your specimen so that you can see the Kikuchi lines as well as your diffracted spot both in your specimen. Kikuchi lines will be used for tilting the specimen and diffraction patterns will be used for the further analysis of your specimen. So the answer for this case will be option C, thinner and thicker. Fine. The next question says convergent beam diffraction is also called as dash beam diffraction. So in convergent, we are converging the beam. So we are making the beam in nanometer regime. So we'll say this. We can also say it as a nano beam diffraction. So option B is the correct answer. The next question says degree of scattering in transmission electron microscope is a function of dash. Degree of scattering in transmission electron microscope. So the scattering will depend upon what? So it's a function of the wavelength of electron beam used, the number and mass of atoms that line the electron path, or the mass of the sample. Anyone? Any guesses for this question number 4? The degree of scattering in transmission electron microscope. So is a function of what? The scattering basically in TM will depend upon the wavelength of the electrons or the mass of the sample or the number and mass of the atoms through which your electron beaming is passed, basically your specimen you can say. Anyone? Any guesses for the question number 4? Are you all there? Yes, option C is very correct, which says that number and mass of atoms that lie in the electron path. Because scattering will depend upon your specimen. If your specimen is having a higher atomic number, then it will interact much with the specimen incident beam, and then you will have your diffracted spot will be of lower intensity because it is interacting and it is less of the electrons are being transmitted and so on. So in the last question says that the mass thickness contrast arises due to dash scattering of electrons. So this mass thickness contrast is basically a combination of incoherent and elastic scattering of electrons. So option D will be the correct answer for this case. And you all must have known that Kikuchi lines is a is due to the inelastic scattering, but your mass thickness contrast is due to incoherent and elastic scattering. Elastic scattering will give you your mass thickness contrast, and inelastic scattering will give you your Kikuchi line. Hope this is fine. I'll move to the quiz of this week 11. If there is any doubt, please let me know. So the quiz, I'll start with the quiz of week 11. So the question number 1 says, why are thin sections of specimen necessary in TM? This anyone can tell. Electrons are negatively charged, electrons have a wave nature, electrons have no mass, electrons have a poor penetration power. Anyone? Why we need thin specimens? This is all we have been discussing from the starting class of TM. We need thin specimen, thin specimen. Why? Anyone? Electrons are negatively charged. Electrons have a wave nature. Electron have no mass, or electron have a poor penetration power. Yes, you are completely correct. Electrons have a poor penetration power. That's why it requires a very thin specimen so that it can penetrate. Because for TM, you need complete transmission of electron from the sample. Fine. So option D is the correct answer. The next question says, which of the following statements is or are true? What should be done right after the TM column is shown to be evacuated? First, insert the sample holder, or further insert the sample holder, remove the dummy holder, or shift the beam. So the first thing need to be done is to remove the dummy holder. So just to maintain the vacuum of the system, this dummy holder is placed when not in use. So you just need to remove the dummy holder and then you can insert your sample holder. This is the second step. So the first step will be option C. The next question says, what type of sample preparation is commonly required for TMNL imaging? For TM imaging, coating with conductive layer, freezing the sample, embedding the sample in resin, or thinning the sample to few nanometer. This any one of you can tell. This is a very clear-cut question. We already discussed the previous question itself. For the sample preparation of TEM, how the sample should be prepared? By coating, or by freezing, or by putting it in resin, or by thinning the sample. Anyone? Any guesses? This is a very simple question, I guess. Please try. There is not no any purpose of me trying to answer all these questions. We discussed. If you are having any doubt, please let me know. Otherwise, please try to answer this question. Anyone, any guesses? For TM, sample should be thinned. So in this case, option D, thinning the sample to a few nanometer is the correct answer. Right? So this is the basic thing which is required for your TM imaging. The next question says, question number 4, the following statement is true or false? We should turn off the light before examination of sample using a fluorescent screen. So you all know, suppose this is your TM column and then you are having a fluorescent screen in below this column, and then you are having your CCD camera or any other camera over here, and you are sitting right here. So you are not directly seeing, you are seeing the image in your monitor itself. So if there is light present in your room, that will, so you are initially you are seeing only this fluorescent screen, that how your sample is tilted or how what features are present in this system. So you if your lights are turned on, that will interfere and you will not be able to see clearly. So you need to turn off the lights of the room so that you can clearly see all the features of your sample. So we should turn off the light before examination of sample using fluorescent screen is true. And someone has also commented, I guess, option A. Yes, you are truly completely correct. Option A, true, will be the answer because we need to turn off the lights because that will interfere when you are looking at your fluorescent screen. The next question number 5 says the following statement is true or false. TM cannot be used to examine live specimen. Is this statement true or false? Anyone? Any guesses? Since the electron beams are very high energy beam, so the live specimen will not be able to survive in the electron beam. So according to me, this statement should be true, that a TM cannot be used to examine the live specimens. The next question says the following statement is true or false. We need to do the alignment of the electron gun beam and rotation center every time we use the TEM. Every time we don't require to do it. If you are doing low mag images or some other bright field dark field images at a lower mag. So the answer will be false. Yes, you are completely correct. I hope you all are with me only. Most of you are commenting. It's very good. So every time it's not required, you just need to check if it is aligned properly. Then you can directly start your imaging in every part. But if you are only wanted to see the low mag images, bright field, dark field, but if you require your HRTM images, high resolution TM images, but if you require HRTM images, then each and every alignment should be very well aligned. So for that, I guess you should align your instrument according to you and then do the imaging. The next question says, fill in the blanks. The specimen requires the vacuum of the order of specimen's vacuum. It's in the range of 10 raised to the power minus 4 to 10 raised to the power minus 6 millibars. Option B. Okay. The next question says, the following statement is true or false. The evolved sphere is smaller in X-ray diffraction as compared to electron diffraction in TEM. This everyone of you can answer, I guess. The eighth question, which says the evolved sphere is smaller in X-ray diffraction as compared to electron diffraction in TEM. Any guesses from anyone? This is a clear-cut question, I guess. We discussed also these evolved sphere comparison. Remember, there was one diagram where this was evolved sphere of visible. This was the sorry. If this is your evolved sphere of your visible line, then this will be the evolved sphere of your XRD. Then this will be the evolved sphere of your electron diffraction, TM. The evolved sphere radius is 1 by lambda. That means smaller the lambda, higher will be the radius. Smaller lambda means higher energy. Higher energy means electron beam as compared to X-ray. So electron diffraction will have a higher evolved sphere as compared to your XRD. So this statement should be true. This you all should answer, no? We have discussed many times that your evolved sphere radius is given by this 1 by lambda. Also, I guess we discussed about the first order low ozone, zero order low ozone. In TM, you can get the zero order low ozone only, while in XRD, you can get 0, 1, 2, 3, and higher order low ozones. The next question says, the following statement is true or false. Kikuchi lines are formed due to inelastic scattering of electrons Within the crystal lattice, is this statement true or false? This I discussed in the previous question itself, I guess. Option A, you are saying true. Okay, anyone else? Is he correct? Is she correct? Anyone? Any other guesses? Yes, you are completely correct. Kikuchi lines are formed due to this inelastic scattering of electrons within the crystal lattice. So option A will be the correct answer for this question. The next question says, fill in the blanks. The Howe-Welhen equation describes the variation in dash of transmitted beam and diffracted beam as a function of crystal thickness. So it tells about the variation in the this we know that this Howe-Welhen equation is used for the thickness contrast. So it basically describes the variation in the amplitude. Option C, variation in amplitude of transmission beam and diffracted beam as a function of the crystal thickness. Okay, I have some few more questions for you guys. These are just the true false question and very simple questions just to clear your basic concepts. So if you have any doubt or any comments for today's class, please let me know. Otherwise, I'll start some other basic questions just for your basic understanding. Just some random questions. These are true or false. I hope you all will be able to answer this, and I'll uh, proceed with these questions only if you will answer. So please try to answer these questions. That will be helpful for you guys. The question number one says, sorry. Yeah. So question number one says, in TM, higher spot size of the beam indicates lower FWHM. Higher spot size. So basically, the beam size is this. Higher the spot size in the beam indicates lower FWHM. Higher spot size means this. So it has lower FWHM as compared to this one. No, this statement is false. Oh, I need answer from you guys, sorry. So in TM, higher spot size of beam indicates lower FWHM. This statement is false because lower FWHM will have a shorter, smaller spot size. Okay. Sorry for the answer of this question. From next question onwards, you guys will only answer. Next question says, we can find orientation information through CBED. Is this statement true or false? These are all just true false question only. You just need to answer true or false. We can find orientation information through CBD. Is this true or false? Anyone? Anyone? Please reply T or F, A or B in the comment section. We discussed about the CBD patterns, no? Yeah, true. Yes, you all are correct. We can find the orientation information through CBD patterns. The next question says, Deviation parameter S is equal to 0 is the best diffraction condition to see dislocation contrast in TEM. Is this statement true or false? I told you that at S is equal to 0, your diffraction pattern will be much more clearer, or at S is equal to uh, when it is outside the evolved sphere, negative. By looking at this slide, you can tell. I hope I have touched slide. Yeah. Anyone? Diffraction pattern will be much more visible when S is equal to 0 or when S is equal to negative. By looking at this diagram, you can tell. Anyone? I'll just go back to the question itself. I hope you all have seen this slide. I'll go back to the question now. Yeah. So anyone, any comments? No comments? After looking at the slide also? This statement is false, no? At S equal to 0, the best diffraction will not be visible, right? At S is equal to 0, best diffraction condition to see dislocation contrast in TM. This statement is completely incorrect, no? Are you all there, no? Is there any doubt? Please let me know. Otherwise, I'll go to next question then, since none of you are responding to question number 3. The next question number 4 says, if the interplanar spacing in real space is f, d, the interplanar spacing in reciprocal space will be 1 by d. This is a child's play question. Any one of you can answer. Any comments? Anyone? Yeah, people are saying Soumya has said true. Yes, its statement is true. The spacing in real space is d, then the spacing in reciprocal space will be 1 by d. So simple. The next question says, Railroads are formed because a feature in a specimen, example precipitate, is elongated in a particular direction. This railroad things we have discussed in the previous classes as well as in today's class also. So this also you can answer that the railroads are formed due to the specimen elongation in a particular direction. Any comments? We have certain few questions. Please reply faster so that we can complete it in today's class. Anyone, any comments? This statement is completely correct, no? So answer will be A, true. If I discuss in the today's class only, if you are having a nano sheet like this, then you are having a nanometer regime in this direction in the height of the sheet, then your railroad will be perpendicular to that. This direction will be your railroads. So this statement is true. The next question says the deviation parameter S is nothing but the distance of the evolved sphere passing through a diffraction spot that is slightly away from the Bragg position and the exact Bragg position. This we discussed in today's class. Any one of you can answer. This is your exact diffraction condition and this is your railroad. So your evolved S parameter is basically what? So when your evolved sphere is passing from this spot or it is passing from this spot, will also giving diffracted spots. And this basically distance is given by this deviation parameter from the exact zone point. This is the deviation parameter. So these are just uh, the definition for the deviation parameter S is nothing but the distance of the evolved sphere passing through the diffraction spot that is slightly away from the Bragg position and the exact Bragg position. This is the exact Bragg position. Okay. So this statement is true. And the next question says CBED in TEM can be used to find lattice parameters of a crystal. Is this statement true? Anyone? Please fast. We don't have enough time for today's class. From CBED, can you tell about the lattice parameter of the crystal? Yes, true. Yes, we can tell. Very good. We'll move to the next question, which says the physical distance at which the wave amplitude is transferred back and forth in a crystal is known as the extinction distance. This is also the basic definition of this extinction distance only. So this statement is also true. So the extinction distance definition is basically what? It is the physical distance at which the wave amplitude is transferred back and forth in the crystal. These are used for the thickness fringes and all. This we have not discussed due to lesser time, but professor have discussed this in his lectures. So I guess you all must have known this extinction distance and what does it tell you about. The next question says the dynamic theory of electron diffraction says that there is an interference between the transmitted beam and the diffracted beam. Yeah, dynamical theory says after the beam is being transmitted, the diffracted beam and the transmitted beam will have some interference and they will result in another wave. So, yeah, you are correct. It is true. Now you are replying. It's nice. The next question says the extinction distance increases with increase in volume of the unit cell. This statement, any guesses? It's false. Extinction distance will also increase with increase in volume because extinction distance is what we discussed in the previous slide only. It's basically the distance at which the wave amplitude is transferred back and forth. So if the wave size of the unit cell itself is increased, then your extinction distance will also increase, no? So this statement which says that extinction distance will decrease if we increase the volume of unit cell, this is false because extinction distance is just the wave or it is there, no? It's basically the wave amplitude which is transferred back and forth in a crystal. So if the crystal size is increased, then your extinction distance will also increase. If they will be directly proportional. So this is incorrect. So this is the last question for today's class. Everyone, please reply to this question. Then you are free to go. The last question says the fringe contrast in a TM image can arise because of variation of thickness or variation of deviation parameter S. This you all should tell. All four of you should tell the answer. This fringes contrast, which we were talking about in today's lecture, will be due to the thickness or due to the deviation parameter S. Any guesses? Anyone? This statement should be true or false. Anyone? I thought all of you will answer, but none of you are answering. This statement is completely true. Yes, yes. Now you all are answering. Fine. So this statement is completely true. So option A will be the correct answer. So with that, I complete my today's class. So if you have any doubt or any comment in today's class, please let me know. Very few students came in today's class. Was there any specific reason? If you have any doubts or any comments in today's class or in the previous classes, please let me know. Thank you, Soumya. Thank you for actively participating in the question answers. Any other comments or any other doubts?